There is a question so old and so fundamental that it predates science itself. It has been asked by philosophers, by priests, by shepherds lying on their backs in fields staring up at the dark. It is a question that every civilization in human history has confronted and none has ever answered. Are we alone? Is there, somewhere out there among the 2 trillion galaxies and the hundreds of billions of stars in our own galaxy alone, another world where something lives? NASA has spent decades and billions of dollars building instruments that approach that question from different angles. But what is coming next is different in kind from everything that has come before. It is a plan, already in development, already drawing on contracts and engineering studies and decades of accumulated knowledge, to point a telescope at a distant star and take an actual photograph of the planet orbiting it, and then read that photograph closely enough to tell whether the air above that planet contains the chemical fingerprints of life. The cost, in today's estimates, is in the range of $40 billion. The payoff, if it works, would be the most significant discovery in the history of human civilization. To understand what NASA is attempting, you first have to understand what the problem actually is. The stars nearest to Earth are, by cosmic standards, right next door. Alpha Centauri, the closest stellar system, is about 2 light years away. That is roughly 25 trillion miles. The planets orbiting the stars in our galactic neighborhood are separated from us by distances that make the entire history of human spaceflight look like a short drive. We cannot send a probe to any of them on any timescale that matters. We cannot visit, we can only look. And looking at a planet orbiting another star is one of the most technically demanding things that human engineering has ever attempted, because the planet does not glow on its own. It shines only by reflecting the light of its star. And its star is, compared to the planet, almost unimaginably brighter. The contrast ratio between a star and an Earth-like planet orbiting in the habitable zone, the region where liquid water could exist on the surface, is roughly 10 billion to 1. Trying to photograph an Earth-like planet next to its star is, in terms of the light contrast involved, equivalent to trying to photograph a firefly sitting next to a searchlight from a distance of several thousand miles, while both the firefly and the searchlight are in motion. This is not a problem that can be solved with a bigger mirror alone. You can build the largest telescope in history, point it at the nearest sun-like star, and the starlight will simply overwhelm any signal from the planet. The planet is there. We know it is there, or at least we know that planets around nearby stars are extraordinarily common. But its light is buried beneath the glare of its host star by a factor of 10 billion. Solving this problem is what the $40 billion plan is designed to do. And the solution involves one of the most audacious pieces of engineering ever seriously proposed. The concept is called a starshade. It is exactly what it sounds like. A large structure positioned in space between a telescope and a distant star, designed to block the starlight before it reaches the telescope's mirror. If you can block the star precisely enough, the planet's reflected light, faint as it is, becomes detectable. The planet emerges from the glare not because you have made it brighter, but because you have made the star effectively invisible. What remains in the image is the planetary signal. And once you have the planetary signal, you can do extraordinary things with it. The starshade design that NASA engineers have been refining for years is not a simple disk. A disk would diffract light around its edges, creating rings of scattered starlight that would still overwhelm the planet. The solution to diffraction is a precisely engineered edge geometry, a shape that causes the light waves bending around the starshade's perimeter to cancel each other through destructive interference rather than combining to create a bright ring. The result is a petal-shaped structure, like a giant sunflower, with dozens of precisely shaped petals extending outward from a central hub. The petal shape is not aesthetic. It is the solution to a wave optics problem derived from careful mathematical modeling of how light behaves when it encounters an edge in the vacuum of space. Every curve of every petal has been calculated to suppress the diffracted starlight to a specific level, a suppression factor that, combined with the telescope's own coronagraph, reduces the stellar glare enough to make the planet detectable. The size of the starshade required to achieve this suppression is staggering. Current designs call for a starshade roughly the size of a baseball diamond, approximately 26 meters in diameter, with petals that add another 26 meters of radius beyond that, giving an overall span comparable to a large sports stadium. This structure has to be manufactured on Earth, folded into a configuration that fits inside a rocket fairing, launched into space, deployed with micrometer-level precision, and then maneuvered to a position tens of thousands of kilometers in front of the telescope. At that distance, the alignment between the starshade, the telescope, and the target star has to be maintained to within about 1 meter, a requirement that translates to a pointing precision measured in fractions of an arcsecond, sustained over observation periods of hours or days at a time. The telescope that the starshade is designed to work with is called the Habitable Worlds Observatory. the central element of what has been known in its planning phase as the Large Ultraviolet Optical Infrared Surveyor, or LUVOIR. The Habitable Worlds Observatory, or HWO, is NASA's designated flagship astronomy mission for the coming decades, identified in the Astro 2020 Decadal Survey, the document produced every 10 years by the astronomical community to set the priorities for space science as the top priority for the field. It is a large space telescope with a primary mirror in the range of 6 meters in diameter, operating across ultraviolet, visible, and near-infrared wavelengths, equipped with instruments capable of taking spectra of the light from individual exoplanets. Spectra are the key. A spectrum is what you get when you spread light out by wavelength, the way a prism spreads white light into a rainbow. Different molecules absorb and emit light at specific wavelengths, leaving characteristic patterns in a spectrum that identify them as reliably as a fingerprint. If you can take a spectrum of the light reflected by an exoplanet, you can read the chemical composition of its atmosphere. And if you find oxygen, ozone, water vapor, methane, particularly in combinations that would not persist in the absence of a biological source, you have evidence for life. This is the science that the $40 billion plan is designed to enable. Not merely detecting that planets exist around other stars, that has been done with thousands of confirmed exoplanets now cataloged, but actually characterizing the atmospheres of Earth-like planets in the habitable zones of nearby Sun-like stars, reading their air, searching for biosignatures, looking through the chemistry of a distant atmosphere for evidence that something is alive on a world 25 or 50 or 100 light years away. The Astro 2020 Decadal Survey did not identify HWO as a priority without first working through the science case with extraordinary rigor. The survey analyzed what would be required to survey a statistically meaningful sample of nearby habitable zone planets, enough to either find biosignatures or constrain how common life is in the galaxy. The conclusion was that you need a telescope capable of directly imaging and taking spectra of roughly 25 Earth-like planets. To find 25 candidates, you need to survey a larger sample, accounting for orbital geometry. Some planets will be in orientations where the star shade cannot separate them from the star at a given time. Working through the geometry of the nearby stellar neighborhood, the survey determined that a 6-meter class telescope equipped with a high-performance coronagraph or starshade system could reach enough target stars to make the survey scientifically meaningful. Smaller telescopes cannot reach enough targets. Larger telescopes would cost significantly more and take longer to build. 6 meters is the size that the science requires. Building a 6-meter space telescope is itself a formidable challenge. The James Webb Space Telescope, with its 5-meter primary mirror, took decades to design and build and cost approximately $10 billion. HWO is a different instrument. Its requirements for optical surface quality are in some ways more demanding than Webb's, because it has to achieve much higher contrast levels to detect planetary light against stellar backgrounds. The mirror surface has to be polished to a smoothness measured in fractions of a nanometer. The telescope structure has to be thermally stable to a degree that eliminates wavefront errors caused by temperature changes. The detectors have to be sensitive enough to detect signals from planets that are reflecting roughly a billionth of their star's light. Every one of these requirements pushes against the edge of what current technology can achieve, which is why the $40 billion figure is not a round number plucked from a budget request. It is the output of engineering studies that have been asking, seriously and in detail, what it would actually cost to build this thing. The starshade adds a layer of complexity that goes beyond the telescope itself. A starshade mission involves 2 spacecraft, the telescope and the shade. They fly in formation, separated by tens of thousands of kilometers, with the shade constantly repositioned to point at whatever target star the telescope is observing. Every time the telescope moves to a new target, the shade has to fly to a new position, which requires propulsion. The fuel budget for a starshade mission is substantial, and fuel is one of the primary constraints on mission lifetime. If the shade runs out of fuel, observations stop. Maximizing the number of target observations within the fuel budget is an optimization problem that mission planners have been working through carefully for years. There is also the question of deployment. A 26-meter petal-shaped structure has to be folded to fit inside a rocket and then deployed reliably in space, where there is no going back to fix a stuck hinge or a misaligned petal. The deployment mechanism has to work correctly the first time and stay deployed for the duration of the mission, potentially a decade or more. Engineers at NASA's Jet Propulsion Laboratory have been building and testing scaled prototype starshades for years, working through the mechanics of deployment, the materials required for the petals, and the structural requirements for maintaining the petal shape to the required precision in the thermal environment of space. The petal edges, which define the optical suppression performance, have to maintain their shape to within fractions of a millimeter across a structure spanning tens of meters. This is not a solved problem, but it is a problem that serious engineering work has made tractable. The alternative to a starshade is a coronagraph. an optical system built inside the telescope itself that blocks starlight, using a series of masks and mirrors. Coronagraphs are not new. They were invented in the 1930s for observing the solar corona, and space-based coronagraphs have been used for decades to study structures around the sun. Applying coronagraph technology to the problem of exoplanet imaging is more demanding, because the contrast requirements are far more severe than anything needed for solar observation. The Nancy Grace Roman Space Telescope, currently in development, carries a coronagraph instrument specifically designed as a technology demonstration for the exoplanet imaging problem. It will not be capable of detecting biosignatures. It is too small, and its contrast performance falls short of what is needed for Earth-like planets, but it is intended to prove out the technology and provide data that feeds directly into HWO design. Every observation Roman makes with its coronagraph is a step toward the $40 billion mission that follows. The integration of coronagraph and starshade technologies is one of the key architectural decisions the HWO mission team faces. A telescope with an internal coronagraph can operate independently, switching targets without the propulsion demands of repositioning a formation flying shade. But its contrast performance is, at current technology readiness levels, somewhat inferior to a starshade system. A starshade provides deeper suppression, but requires the second spacecraft and its fuel budget. The most likely architecture for HWO involves an internal coronagraph as the primary observing mode, with a starshade available for the highest priority targets where the deepest contrast is needed. This gives the mission flexibility without depending entirely on the more operationally complex starshade system for every observation. What would it actually look like to discover a biosignature? The process would not be a single dramatic moment. It would unfold over months of observation, analysis, verification, and peer review. The telescope would spend many hours staring at a target star, while the starshade held its position with extraordinary precision. During that time, photons from the planet would accumulate on the detector. Not many, but enough over sufficient integration time to build a spectrum. The spectrum would be analyzed for the presence of atmospheric gases. A detection of oxygen alone would be interesting, but not conclusive. There are abiotic processes that can produce oxygen. A detection of oxygen and methane together is far more significant, because these two gases react with each other chemically and should not coexist in the same atmosphere unless something is continuously producing one or both of them. Life is the most natural explanation for that continuous production. A detection of water vapor alongside oxygen and methane in a planet orbiting in the habitable zone of a sun-like star would represent the strongest possible biosignature signal that spectroscopy from this distance could deliver. Even then, the scientific community would not immediately announce the discovery of life. The first detection would trigger a process of independent verification. The same target observed by multiple instruments, the same data analyzed by multiple teams, alternative abiotic explanations exhausted one by one. Science moves slowly and carefully when the stakes are this high. But eventually, if the signal held up, there would come a moment when the accumulated evidence pointed in only one direction. And that moment would divide human history into a before and after more sharply than any event in recorded memory. The $40 billion figure sounds enormous. In the context of what it is attempting to purchase, it is worth examining carefully. The United States spends roughly $800 billion a year on defense. The Apollo program, adjusted for inflation, cost around $280 billion and put 12 people on the moon for a few hours at a time. The Hubble Space Telescope, over its lifetime, including servicing missions and operations, has cost roughly $16 billion and transformed humanity's understanding of the cosmos. HWO, at $40 billion, spread across the better part of 2 decades of development, operations, and science, is not an extravagance. It is an investment in answering the oldest question our species has ever asked. Every dollar of it goes toward building the first instrument in history with a realistic chance of detecting life beyond Earth. Whether that detection comes or not, whether the planets we image turn out to be barren or alive, the knowledge, produced by looking closely at dozens of Earth-like worlds, will reshape science, reshape philosophy, reshape the human understanding of our place in a universe that is either full of life or, in the most profound way imaginable, waiting for us to fill it. The mission does not have a launch date yet. It is in the phase that engineers call pre-formulation, the period of studies, trade analyses, technology development, and cost refinement that precedes the formal start of a mission. The technology it requires is not all mature. The mirror fabrication techniques need further development. The coronagraph contrast levels need to be demonstrated at flight representative scales. The starshade deployment and formation flying systems need extensive testing. All of this work is happening, funded through a technology development pipeline that feeds directly into the eventual mission design. The target is a launch in the early 2040s, far enough away that the work ahead is substantial, close enough that the people building the technology today will live to see what it finds. What it finds, maybe nothing. The habitable zone planets around nearby stars may turn out to have no biosignatures, or to have atmospheres so different from Earth's that our biosignature models do not apply cleanly. The survey may reveal that life, while possible on worlds like Earth, is rare enough that none of our nearest neighbors host it. That result would itself be a profound scientific finding. It would mean something about the distribution of life in the cosmos, something about the filters that separate simple chemistry from the organized complexity of biology, something that would force a re-examination of every assumption our science has made about the prevalence of life. But there is also the other possibility. There's the possibility that within the lifetime of people alive today, the spectrum of a planet 40 light years away will reveal oxygen and methane and water vapor in proportions that no purely geological process can explain. There is the possibility that NASA's $40 billion plan will work exactly as designed, and that the answer to the oldest question our species has ever asked will turn out to be, no, you are not alone. You never were. None of this happens without people choosing to work on it. The engineers spending their careers refining the optical surface quality of mirror segments that will not fly for 20 years. The mathematicians deriving the petal shapes that will govern how light bends around a star shade in vacuum conditions they can only partially simulate on the ground. The astronomers cataloging the nearby stellar neighborhood, characterizing the stars that will be HWO's target list, determining which ones are stable enough that their brightness does not fluctuate in ways that mimic or mask planetary signals. The instrument scientists building the detectors and spectrographs that will have to catch and measure a planetary spectrum faint enough that a single photon from the planet arrives at the mirror perhaps once every few seconds. All of them are working toward a single moment they may or may not live to see. A moment when a spectrum on a screen, accumulated over hours of observation, shows a pattern of absorption lines that means something is out there, breathing, living, existing under a sky, orbiting a star that is just another point of light from our vantage point on Earth. The philosophical weight of that moment is difficult to hold in the mind. For all of human history, the question of life beyond Earth has been exactly that, a question. It has been answered by religion, by mythology, by speculation, by science fiction, but never by science, never by evidence, never by data collected from the real universe using instruments built by human hands. The HWO mission is the first time in history that humanity will have a purpose-built scientific instrument with a realistic, quantified probability of detecting life on another world. Previous telescopes have been extraordinary, but they were not designed for this. Hubble was designed to study galaxies and stars. Webb was designed to see the earliest light in the universe. HWO is designed from the mirror size to the coronagraph contrast level to the spectral resolution of its instruments, specifically and primarily to answer the question of whether life exists elsewhere. That focus is unprecedented, and it carries with it a weight that the people building it understand very clearly. The search also has a second dimension that receives less attention than the biosignature hunt, but is scientifically profound in its own right. Even if HWO finds no biosignatures, it will produce the first actual photographs, not artists' impressions, not orbital detections, but real images of Earth-sized planets around other stars. Those images will show us, for the first time, what other Earths actually look like. Whether they are blue, like our ocean-covered world, or red, or gray, or banded with cloud systems visible, even at the resolution available from tens of light years away. The color of a planet encodes information about its surface and atmosphere. A world covered in liquid water looks different from a world covered in desert rock or ice. Even without spectroscopy, the color photometry of these worlds will tell us whether they are likely to have oceans, whether they might have seasonal vegetation cycles, whether they are shrouded in thick cloud cover. We will see these worlds, really see them, for the first time. And seeing them will change what they are to us. They will become places, not numbers in a catalog. There is also what the mission will teach us about our own world. Every time scientists develop a model of what an inhabited planet's spectrum should look like, they are forced to confront how much of what makes Earth detectable as a living world from a distance is unique to Earth and how much is general to all life. This forces deep questions about the nature of biology itself, about which molecular processes life tends to settle on, and which are contingent accidents of our particular evolutionary history. Understanding what a generic biosignature looks like, rather than an Earth biosignature, is one of the foundational challenges of astrobiology, and the process of designing HWO's instruments and observation strategies has been pushing that science forward at a pace that would not have been possible without the concrete engineering deadline the mission creates. The mission also has geopolitical dimensions. The European Space Agency has been developing its own concepts for direct imaging missions, and the scientific community has spent years discussing how international collaboration could amplify what any single agency could accomplish alone. A joint mission between NASA and ESA could share costs, share launch vehicles, share science operations, and produce a scientific return larger than either could achieve independently. The discussions are ongoing, and the final architecture of what gets built in the 2040s may look different from what is being planned today. But the direction is set, the technology is developing, the science case is made. The only remaining questions are engineering, funding, and time. Time is the one resource that cannot be manufactured or supplemented. The people who will operate HWO, who will sit at consoles and watch the first spectra of habitable zone planets accumulate on their screens, are in their teens and 20s today. They are studying physics and astronomy and engineering without knowing yet what role they will play in the most consequential scientific mission in human history. The people who are already in the field, already working on the technology, will in many cases retire before the mission launches. That is the nature of projects at this scale. They outlast the careers of the people who start them. They are bets placed not on the present, but on the future, on the judgment that the question is worth the time, that the answer, whatever it turns out to be, is worth $40 billion and 20 years of the best engineering talent our civilization can direct toward a single problem. It is worth it. Not because we are certain to find life, we may not, but because the capacity to ask the question with instruments rather than imagination, with data rather than philosophy, with evidence rather than faith, the capacity is itself one of the highest expressions of what human intelligence can achieve. We evolved on one small world under one ordinary star in one outer arm of one average galaxy, and we built tools powerful enough to read the air of worlds orbiting stars dozens of light years away. Whether those worlds turn out to be alive or not, the act of looking is extraordinary. The act of looking is what we are. And the $40 billion plan to image alien worlds is, at its deepest level, not a space mission. It is a declaration, made in steel and glass and silicon and mathematics, that we are a species that refuses to stop asking the question. The road to launch will not be smooth. Large NASA missions of this scale have historically suffered from cost growth and schedule slippage, and HWO will face pressures that no amount of careful planning can entirely eliminate. The political environment in which space science funding exists changes with every administration and every budget cycle. The engineering challenges of building a 6-meter telescope with coronagraph performance orders of magnitude beyond anything previously demonstrated will produce surprises. Technology development programs will encounter dead ends and have to backtrack. The Starshade formation flying system will require tests that reveal problems, that require solutions, that take time to develop. This is not pessimism. This is what the history of ambitious space missions looks like. It is also, always, what eventual success looks like, because the missions that produced the greatest science were invariably the ones that overcame the greatest obstacles. Hubble's mirror was polished incorrectly, and the repair that fixed it produced a moment of triumph that became one of the defining images of modern science. Webb spent years behind schedule and billions over budget, and it then delivered images of the early universe that left astronomers speechless. HWO will have its own version of these struggles. It will also have its own version of the triumph on the other side. The cadence of discovery the mission will produce, once it begins operating, is almost impossible to fully imagine from the vantage point of today. In the first year of science operations, HWO will observe dozens of nearby stars. Some of those observations will reveal planetary systems. Some of those systems will have planets in the habitable zone. Some of those planets will be close enough in size and orbital characteristics to Earth that they enter the priority target list for spectroscopic follow-up. And then the spectra will begin to come in, one planet at a time, each one a world that no human instrument has ever characterized before. The process will be methodical, the science rigorous, the conclusions carefully qualified. But the accumulating picture, planet by planet, spectrum by spectrum, will be something that has never existed before. A catalog of other Earths, each one described not just by its orbital period and estimated size, but by the composition of its air. Some will have thick carbon dioxide atmospheres. Some will have no atmosphere detectable at all. Some may have water vapor in quantities that suggest surface oceans. And perhaps one, perhaps more than one, will show the combination of signals that points, after every alternative has been ruled out, to something living there, breathing there, existing in the light of a distant sun on a world that until that moment existed only as a number in an exoplanet database. That is what $40 billion is being aimed at. That is what the engineers and scientists and mathematicians are working toward in laboratories, in conference rooms, and computing clusters right now, today, while most of the world goes about its business, unaware that the most important scientific project in human history is already underway. The Starshade petals are being shaped, the mirror technologies are being refined, the coronagraph masks are being tested, the target star catalog is being assembled. The question has been asked for as long as we have been human. The answer is being built. The scale of what is being built also forces a reckoning with something that space science rarely discusses openly: the possibility of a negative result and what it would mean. If HWO surveys its full target list, if it images and takes spectra of 24 Earth-like planets in habitable zones around nearby Sun-like stars, and finds no biosignatures in any of them, that result is not a failure of the mission. It is a finding of extraordinary scientific importance. It would suggest that life, at least in the form that produces an oxygen, methane, water atmosphere on a rocky world, is rare in the universe even among planets that meet the basic physical criteria for habitability. This would have profound implications for our understanding of the origin of life. Implications that would reshape biology, chemistry, and our understanding of the path from simple chemistry to the organized complexity that characterizes living systems. The Fermi paradox, the observation that if life were common, we should have detected signs of intelligence by now, has haunted space science for decades. A negative result from HWO would not resolve that paradox, but it would sharpen it considerably, and it would tell us something about ourselves, that Earth is not typical even among Earth-like worlds, that the conditions that produced us were more improbable than the simple abundance of potentially habitable planets would suggest. Equally, a positive result, even a single confirmed biosignature on a single world, would resolve the debate that has defined astrobiology since the field's inception. It would mean that life arises independently more than once in the universe, and if it arises more than once, the logic of large numbers says it arises everywhere, on billions of worlds across billions of galaxies across a universe 13 billion years old. The step from one confirmed independent origin of life to the conclusion that the universe is full of it is not certain, but it is the most natural inference from the data. One detection would not just tell us about one planet, it would tell us about the nature of the universe itself, that it is, at a fundamental level, a universe that produces life wherever the conditions allow. These are the stakes. They are not overstated. The Habitable Worlds Observatory, whatever its final name and final form, is pointed at the deepest question our species has ever formulated. The $40 billion is not the cost of a spacecraft. It is the cost of an answer.